Hello. Cholesky factorization is the most known LU decomposition method, specifically in solving the systems of linear equations with symmetric coefficients matrix. In this tutorial, you will learn the conditions required in those systems, how to formulate Cholesky's algorithm, and how to apply it by using a Python code. Decomposition or factorization in mathematics means to resolve or break a value down to two or more components. These components can compose the original value if they are added or multiplied. Solving linear systems using matrix decomposition requires a specific structure of the component matrices, because after the decomposition there are other procedures to be applied in order to get the solution. This specific structure is known as LU, or lower upper matrices, and the methods used to get them are called the LU decomposition methods. In these methods, a given matrix of coefficients A is resolved to two square matrices of the same size. The first is called the lower triangular matrix, which all non-zero elements lie on and below the main diagonal. The second is called the upper triangular matrix, and it has all non-zero elements on and above the main diagonal. This operation can be written in a simpler notation, such as that the matrix A is equal to the inner product of L and U. You should remember here that the matrix multiplication is not commutative, which means L multiplied by U is not equal to U multiplied by L. Cholesky decomposition, or as more known as Cholesky factorization, is applied to the matrices with special conditions. First, the matrix should be symmetric. Second, it should be positive definite. The condition of symmetry makes the computation of the lower triangular matrix enough for factorization, because the upper matrix is simply the transpose of the lower matrix. Consequently, the components of the matrix A will be L multiplied by LT, or L transpose. The two requirements or conditions of Cholesky factorization must be satisfied before applying the method. First, let's speak about the symmetry. The matrix is described as symmetric if it is a square matrix and the elements are mirrored above the main diagonal. This can be represented by using element indices as Aij is equal to Aj for all I and j. For example, this matrix is symmetric because every element about the main diagonal is reflected below it. Let's check some elements. A12 is equal to A21, which are equal to 0. A23 is equal to A32, which both are equal to -2, and A14 is equal to A41, which are both are equal to 4, and so on. Therefore, it's obvious that a symmetric matrix should be equal to its transpose. A real matrix A is positive definite if the product of its multiplication from the left side by a vector Z transpose and from right side by vector Z is always positive for all real number of Z except 0. This is a mathematical definition. Let's see an example. The identity matrix is positive definite. So if we carry out the multiplication shown here, the result will be Z1 square plus Z2 square, which is always positive for any real value of Z1 and Z2 except 0. The method of vector matrix multiplication shown here is not practical to test whether the matrix is positive definite or not. An easier way is to apply the following rule. A matrix is positive definite if and only if all of its eigenvalues are positive. So, the definiteness of a matrix can be tested by using eigenvalue functions from the linear algebra module of Numpy. In this example, I will show you how to use the functions of eigenvalue in Numpy in order to test the positive definiteness of the matrices G and H. As you see here, we have defined the matrices G and H. So now let's test each matrix for positive definiteness. So first, we can use the, let's say, import. Then this function returns the eigenvalues of a given matrix. So let's test the G matrix. Let's see. We have the eigenvalues of the G matrix, and as you see, all elements are positive except number 4, or the fourth element, which is negative. So that means we cannot decompose this matrix by using Cholesky decomposition method. We can use another function. This function is more comprehensive than the first one because it returns both eigenvalues and the eigenvectors. So as you see, the eigenvalues are the first row of the output. In order to get the first row only, we can make a simple trick here. Now, this shows that we have a tuple of V and underscore, because we don't need the matrix of eigenvectors, so that's why we assign it to the underscore, while if we try to return the value of V, we get the eigenvalues of G. And as you see, it's the same result. Now let's test the matrix H. So we can say by the same way, the all values of the eigenvector of the matrix H are positive. So that means this matrix can be decomposed or factorized by using Cholesky's method. The algorithm of Cholesky factorization can be developed simply by multiplying the symbolic components L and LT, then equating each element in A with the corresponding element in the product matrix, as you see here in this 4 by 4 matrix. Because both matrices are symmetric, the algorithm can be formulated by using the elements in the lower triangle. The formulations goes column by column, so we start with the column 1. First, we get the element L11, then L21, which is calculated using L11. The same thing is done with L31 and L41. The elements of the column 2 of the lower matrix can be found by using the calculated elements in column 1. The element L22 is found by using A22 and L21 from the first column and second row. L32 is found by using A32, L31 and L21. L42 can be found also in the same way. Similarly, the third column can be found in the same way by using the elements of L from the previous 2 columns, and so on. The last column should have only one element on the main diagonal, and as you see, it is found by using all elements in the last row found before. Now, by close look into the indices of each element in these formulae, we can find the general pattern of each row and column. For example, the L-squared terms and calculations of L22, L33, and L44 have the fixed index of the rows, while the second index, as you see here, goes from 1 to the number of rows minus 1. Similarly, patterns can be seen in other elements with different row and column numbers. That helps us to write the general formula of Cholesky's algorithm. The algorithm consists of 2 nested loops. The J loop is the outermost loop, and it goes through all of the columns, since the calculations, as I told you before, should proceed column by column. Next, the I loop starts at row J to compute the elements on the main diagonal and the lower ones. The first formula is for the elements on the main diagonal, where I is equal to J. while the second formula is for the elements beneath the main diagonal. Each formula requires an internal loop for summation. This can be done by utilizing a k-loop or by using Numpy sum function with slicing, as I'll explain during the coding. In this example, we have the matrix H, which we have proven that it's positive definite. But for comparison, I will try factorizing the matrix G2 and show you the results. So let's go to the editor and start coding. So we begin by importing Numpy module. Then we define the function Cholesky with one argument, which is the matrix A, where A is a Numpy array. Then we define the lower triangular matrix. This function constructs a zeros matrix or zeros two-dimensional array and the same size of A. Now we need the size of A. We can use the function shape. Since A is a square matrix, so it's enough to know the value n, which is number of rows. Now we start the loop of columns, then the inner loop. Now we have two formulae. Let's start with the first. We initialize the summation variable. Let's call it sum k. And we start inner loop of summation. So Lij for the main diagonal elements will be equal to the square root. Let's go to write the second. So else, the same way, finally, we return the lower triangle. Now let's test this function by decomposition of the matrix H. In order to save time, I copied and pasted matrix H. So let's run the function by saying that L Now, in order to verify our result, we can simply multiply this matrix by its transpose. So, let's say, so mp dot is dot product function of multiplying two matrices. So the first matrix is L. The second will be, so if we compare the values of the resulting matrix, we notice that they are the same values we defined in the code. So let's try G in this example. I'll copy paste it in order to save time. Now we define G and passed it as an argument to the Cholesky. So let's run the code and see the result. So as you see here, we have error message or warning message due to the square root function. So that's why you notice, if you remember, that the fourth element in the eigen values were negative. And here we see that the problem started at the fourth row and fourth column. Now, before end in this video, let's use the slicing and sum function from Numpy. So instead of using sum k, we will use Numpy sum function. So we say sum, and then, but we notice something here. Still we have k, but k is a loop which goes from, let's say, from beginning to j. So we can use slicing here, which is, and then we do the same thing with this part. So instead of this, we say Numpy sum. Again, for the k, we say for j. So in this way, we reduce the size of the program. Let's try to run the code again. Let's go back to H here in order to get done. So as you see, we have the same result. In order to be sure, let's again make the multiplication. And as you see, we have got the same original matrix H after the multiplication of L and LT. In the part 2, I will show you how to solve a system of linear equations by using Cholesky factorization. If you like this video, please hit the like button, and to be notified for the coming videos, subscribe and hit the bell. Thank you for watching.